I'm Alan Willison, the chairman. It's my pleasure to see you all here. I know we've got quite a few new people with us this evening. Please don't go home without saying hello to us, the people who are around here. We want you to know we are a friendly bunch, and we obviously want you to come again and at another meeting. I also know we've got some new people on Zoom. I believe one of them is even as far as Lytham St Hans. So welcome to you as well. It's lovely to see so many people. I think we had 17 on Zoom and we've got quite a big crowd here. So it's lovely to see so many of you. The format of the evening is Martin will give us a talk in a few moments' time about the night sky. That'll be about 10 minutes or so long. And following that, Jerry will introduce tonight's speaker, who's going to talk to us about eclipses. The talk will last round about an hour. You will be able to ask questions. If we ask that you keep the questions until the end of the presentation, and then for those of you in the university, we will come round with a microphone so that you can ask your question and the people on Zoom will be able to hear it. For those of you on Zoom, if you wish to ask a question, you can submit it through the chat facility and the question will be read out here. So that's enough from me. I'm now going to pass you over to Martin for his presentation.
Right, so starting of spring. So I've just really given a little bit of a brief talk about what we can see through the next couple of months. I took this picture off of the internet because I thought it was quite a nice image that was taken in Scotland. We can see a little bit of the aura and we can see the night sky there as well, Mars and Venus also. So I think it's quite good the way they've got the old-fashioned telephone box lit up there as well. So I don't know if they still use them or not in Scotland, but quite a nice image, I thought. So moving on, so on Thursday, March the 20th, it's the equinox. This is the point where the sun has reached a point where we get equal amount of light and darkness. So there's a little picture there showing the sun at the equinox position. So the northern latitudes on March equinox, the amount of daylight is equal, peaks at 3 minutes. So we can look forward to now some more light, which is good for getting out and doing a few bits and pieces, but not so good for us astronomers. We prefer the winter, especially when it's nice and clear. I'm not going to talk too long about eclipses because that's the main brief by our talk tonight. So, but I thought I'd just mention as a part of the lunar eclipse, which is due on the 14th of March, which is just a couple of days away, on Friday. If we've got a clear, I think it's in the morning, so you need to get up to see it, and it actually goes full when it goes below the horizon, which is why we only see a partial eclipse. But I stuck a few pictures up I picked off the internet, which I thought were quite nice. This one here of it, you can see the sun line there going through, and it's slowly coming down in a curve, and then full covering the moon at that point, or covering the Earth is covering the sun and making the moon go a reddy orange colour. So there we are. There's the layout. So 3:57, the moon moves into Earth penumbra, and the moon moves into Earth shadow at 5:09, and then 6:19, just before it drips down below the horizon, we'll get the maximum eclipse that we're going to see from this latitude. So if it is, I'm probably just going to look out the window. If it's clear, I'll go out. If it's cloudy, I won't bother. A bit early in the morning. So yeah, I put this picture up. Steve took, one of our astrophotographers, back in 2015, and I thought they were rather decent images. You can see quite a bit of the lunar surface as well. So, also a partial solar eclipse on the 29th of March. Again, it's only partial for us. It's sort of out in the Atlantic where it become a full eclipse, just off the eastern seaboard of America. But I just thought I'd mention it. We will get a bit of, if we've got a clear day, we'll be able to see something like that. And another picture Steve took of the eclipse. I don't know what year this was, Steve. 22. So, and that even made the cover of a Electric Enemy band. Whoever, I'm not familiar with them, but they're a band. But a spectacular picture all the same. I am sort of heavily looking at the imaging tonight because I can. So also the Lyrid meteor shower is coming up. Stole that picture off of the internet, which I thought was rather good. It's good to have a background, something you can gauge it by. But the Lyrids, well, perhaps a bit early to talk about them, but 22nd of April is the high point for the shower. And I expect to see up to 100 meteors per hour. So the Lyrids, because it's coming from a comet Thatcher, which was some time ago, that we're passing through the remains of its tail. I don't think it's anything to do with Mrs. Thatcher, but as the bits of ice and dust enter the atmosphere, they burn up and create streaks of light. So if you are an opportunity to go and have a look on that evening, if you look in the constellation, if you look for the bright star Vega, which will be a bit more predominant by then in the eastern sky, then you'll see hopefully some meteorites. Also, Aurora Borealis, the sun is still in its peak of activity in its 11-year cycle, so hopefully a clear night we should see more activity. I mean, last year we were seeing it right down in the southern reaches, right down on the south coast, so maybe another year could have some more interesting displays of Aurora Borealis. Okay, so I'm going to talk about astrophotography a little bit now because we've had a week and a half, 10 days of clear nights, the first time for absolute age, and our astronomy group, astrophotography group, have been really active. So I've started to put a bit of a presentation as myself and Steve there. If any of the other members of the Astro group want to send me a picture with a telescope, I'll put them on here and we'll make up a bit of a rogues gallery of astrophotographers. So the first image, one of Steve's. I thought this was absolutely cracking image. So this is M82, a beautiful galaxy. You can see an awful lot of dust lanes in there and information. There's some new star growth areas where the hydrogen alpha lines are running through there. But a tremendous amount of activity going on in that galaxy, a lot of star birth. Next image is one of Steve's as well. This is M78. This is a reflection nebula in Orion, not actually imaged too often because it's not particularly bright, but it's in that particular area. It's probably the brightest bit of a diffused reflection nebula. So Steve's got some really good detail in there. I don't know how much time you spent on that one, Steve, but it's certainly come out well. You ought to read it, I suppose. This is one of mine. This is quite a dim nebula, and it's not often imaged, so which is why I took the opportunity to have a go at it. In fact, I've been looking at some of the astronomy photography section pages on the internet, and I haven't found another one of this particular one. Well, only ones that were taken by NASA, so I'm quite pleased with the results on that one. Anybody interested in astrophotography, do contact either myself or Steve or Dennis or anyone else in Haggas. We've also got a web page, a Facebook page where we all put up our pictures. So if you're interested, do come and have a look. Now this is Bode's Galaxy, another image of Steve's taken 12 million light years away, a bit further than Andromeda. But again, the detail within this galaxy, the stars you're actually seeing as dots aren't actually in that galaxy, they're in our galaxy. They're in front of it. These galaxies are so far away you can't see individual stars unless they go supernova. And then that is the time that we can actually make out the stars in the galaxy itself. So yeah, those white dots you can see there are actually in our Milky Way. This one here, Steve has won a prize. Well, not won a prize, but he's certainly given the object of the month in UK Cloud Magnets, which is a really big Facebook group for astrophotographers. So well done, Steve. This is a really difficult object. The Eskimo Nebula is really faint and really small. So well done and well deserved accolade. Always got to have a picture of Jupiter. So this is one that Michael took. His pictures of Jupiter are just absolutely stunning. Watch out, Damien Peach, I think I should say. But yeah, so that's quite good. No red dot on that, no red spot on that one. It's obviously round the back. Jupiter turns every 10 hours in its rotation, so the faces are changing quite quickly. This is a brilliant image of the Leo triplets. These are 3 galaxies in our local group. And galaxies are quite faint, so as Steve's living in a Bortle 7 area sky, which is pretty bright, pretty light. So to get such detail on those galaxies, I think, is absolutely first class. So hopefully you can recognise this image. It's the Pillars of Creation that Hubble made famous with its brilliant image, and I know that it's been imaged by everybody, but this is my attempt to try and capture the pillars themselves, the part of the Eagle Nebula. Yeah.
You actually compared it with the Hubble map?
Yeah, to get the colours, I did. Yeah. Yeah. I use the Hubble palette.
So that's really good colour.
Yeah, I use the Hubble palette, which is called false colour. But the reason is we use these particular colours is they give you this 3-dimensional effect that you get with it. They give you a depth. Yeah, that's the main reason for using that particular palette. But if you took it with a colour camera, it wouldn't be that colour at all. So yeah, I use 3 different filters. I use a hydrogen alpha, oxygen 3 and a sulfur 2 at 3 nanometers bandwidth, so I only allow light in that bandwidth to come through, which means I have to do really long exposures, but I think you get rewarded with so much more detail. This is a Seagull Nebula. I've never attempted this one before, so quite pleased with the results. It does look like I've got it not in frame completely there, because I actually used 2 telescopes, and my main telescope is only taking the actual central part. It's only taken that bit there. So my main telescope's only imaging that, so that's why it's in the centre. But I have another telescope, it's on a piggyback, which has done this image, and actually preferred that one to the one I took with my big telescope. So that's the one I've imaged. This is a new planetary nebula that one of our members, Peter Cadieu, has a fantastic setup in Spain where he hunts and looks for new planetary nebulas, and this is one that he discovered or was pointed to. And what the time is on that? I don't know if it tells me on that one. 60 hours. 60 hours of imaging in Spain to get that. Just shows you how dim it is.
Wow, it sounds like a very complex science, but the results are absolutely fantastic. So thank you very much, Martin, and everybody who contributed to that presentation.
And
Amazing.
anybody wants interested in astrophotography, come see me, Steve, or Dennis, over there, and we'll guide you on what you can do.
Okay, those of you who want to get started, these are the people to speak to. Okay, I'm now going to pass you over to Jerry, our programme secretary, who's going to introduce tonight's speaker.
Thank you, Alan. Oh, well, when I first discovered that there was going to be an eclipse of the sun, partial eclipse, and it was going to be a Saturday morning, basically from 10 till 12, I thought, oh, fantastic. We've got to do a public event for that. And the obvious thing was to have someone at our talk, at our meeting beforehand, who would talk about eclipses. So I looked around and it seemed the obvious person was Mike Foulkes. He is, he runs the British Astronomical Association section for Saturn, Uranus and Neptune. And he is a keen astrophotographer himself. The description that is on our website, it says at the bottom, he has worked in the space industry, and he may enlarge on that a bit. But will you please welcome Mike Foulkes.
Thanks, Jerry.
Thank you.
All good. Well, good evening, everybody. It's very nice to be asked to give a talk here at HAG, and especially in this wonderful lecture theatre. It's just like being back in student days years ago, but it's really nice and it's very comfortable indeed. I'll start off. It was in 1929 that Edwin Hubble published his famous paper about galaxies that seem to be further away, seem to be moving faster and faster away from us. And this led to the ideas of the expanding universe and the Big Bang, which was a term coined by the famous British astronomer Sir Fred Hoyle as a term of derision, because he didn't like the idea of an expanding universe, but the Big Bang has stuck. And since that time, our knowledge of the universe has gone on enormously. We've studied the universe at not just at optical wavelengths, we go from gamma rays up to radio waves. We've even now managed to detect gravitational rays, ripples in space-time. Discovered all sorts of weird objects like black holes, neutron stars, gamma ray bursters and such like. So we've come a long way since Edwin Hubble wrote his paper. There's certainly a lot of things we don't understand about the universe. What is dark matter and dark energy in any case? But one thing we can say with certainty, everything seems to be in motion. As we've sat, or in my case stood in this room, we're on the Earth, which is spinning on its axis, which in turn is going, the Moon and the Earth are going around the common centre of gravity. We're orbiting the Sun is orbiting the galaxy. Some of the galaxies are in orbit around each other, we've got stars going around each other. So it seems a reasonable assumption to think that from some vantage point or another, we're going to see one object pass in front of another. Now, for objects that are squillions of light years away, it's going to take geological timescales. But some things can be seen in more human timescales, even down to just a few seconds. So what do we call these things in astronomy? Well, astronomy, being astronomy, has got three terms which describe essentially the same sort of thing when one object passes in front of another. And the first term is called an occultation. And an occultation is where a body which appears larger in angular size passes in front of one that's smaller in angular size. And the classic thing about an occultation is the moon. It occasionally passes in front of stars. So even though stars are hugely larger than the moon, this is what an occultation, the moon appears larger in the sky, angular terms. The moon also passes in front of planets from time to time, so we get occultations of the planets. In fact, over the last couple of years, this one was taken a few years ago, we've had an occultation of Mars, we've had another more occultations of Saturn. The second term is called a transit. And for many people, the word transit means, travelling. And for a lot of people, the word transit means one of these things. Beloved by, or its later models and other manufacturers, beloved by white van man and white van woman, DPD drivers, Amazon drivers, and so on. But for astronomers, the word transit has a couple of meanings, but in this context, it means this, which is the complement of an occultation. In this case, it's a body that's smaller in angular size, goes across one that's bigger. And the classic example of this are transits of Mercury and Venus. And here is a picture of Mercury going across the Sun, which is that small object. You can see Mercury there, press the wrong button. And then we get transits of Venus. Venus has been a bit closer to the Earth, bigger than Mercury, appears a lot bigger. And these are quite rare astronomical events. For Mercury, there's about, a dozen transits a century. For Venus, however, it's a very rare astronomical event. One appears every 125 years or so, separated by 8 years. So these are quite rare. But the third term is what we're really going to be talking about tonight, which is eclipses. And there are various definitions of what an eclipse means, and some of these are taken from books, some are taken from the explanatory notes of the Astronomical Ephemeris, and they sort of cover that it's one body passing in front of another. The interesting one is where one body goes into the shadow of another one. And the word eclipse comes from a Greek word, ecliptis, and indeed we'll see this word cropping up from time to time as well. But certainly amongst eclipses, the two most famous ones, which have already been alluded to tonight, are eclipses of the Sun and eclipses of the Moon. Now, I'm sure many of you know the mechanism behind eclipses of the Sun and eclipses of the Moon, but it's worth recapping on that. By a lovely coincidence, although the Moon is 400 times, give or take, smaller than the Sun is 400 times further away. So from our perspective, they appear very much a similar size in the sky, roughly about half a degree. And from time to time, the Moon will pass, from our perspective, in front of the Sun and will cover the Sun completely. And this is a total eclipse of the Sun. It hides the bright disk of the Sun that we see, which is the photosphere, incredibly bright, and it allows us to see some of the atmospheric features, the outer atmospheric features of the Sun, such as the corona, prominences, the chromosphere, and so on. The Moon shadow is divided, like all shadows, into two bits. There's an inner core, which is the umbra, and if we observe from inside the umbra, we would see a total eclipse. The outer core is the penumbra. Sorry, I jumped ahead again, sorry. Is the penumbra, and from here you'd see a partial eclipse. So the deeper you go into the penumbra, you see a bigger partial eclipse. As these sweep across the Earth's surface, they define a track. Now the track of the umbra, where we see a total eclipse, may stretch for several thousand kilometres across the surface of the Earth. However, it's relatively narrow. At its maximum, under the best of conditions, it may be about 250, 260 kilometres wide. And often it's a lot less. Further, as we get to the edge of the Earth, the shadow will be narrow, because on this side of the Earth it's further away from the Moon than underneath the Moon itself. So it does vary along that. So this is one of the reasons why total eclipses of the Sun are so weird. The tracks across the Earth are relatively small. However, the penumbra is quite large. Typically, its diameter is about 6,500 kilometres across. And so with this, often as not, we'll get a penumbral eclipse across large parts of the Earth's surface. In fact, in some cases, some people may only see a penumbral eclipse. If we have a total eclipse of the Sun where the Moon covers the Sun, given our earlier definitions, that could possibly considered to be an occultation. Now the moon, one complication is that the moon and the sun, the moon distance from the Earth varies over its orbit, and the Earth's different to the sun varies over its orbit. So the apparent diameters of the sun and the moon do change over the year. And typically, these are typical values that show the distances of the sun from the Earth and the moon from the Earth when they're at the closest and furthest away. And this results in a change in the angular sizes. For example, when the moon is at closest, at perigee for example, we can see that the angular size is 33 arc minutes, 30 arc seconds. For those of you who are not familiar with the terminology, an arc minute is a 60th of a degree, and an arc second is a 60th of an arc minute. So an arc second is actually a very small angular size. And the change in angular size for the moon is a lot bigger than the sun. So there are occasions, even if we get everything lined up correctly, the moon won't cover the sun completely. In this case, what we get is an annular eclipse. Annular is for a ring, and the moon, the photosphere won't be covered. You get a bright ring left around the moon. This shadow where we see an annular eclipse is called the antiumbra. Sorry, I've jumped again. Apologies about that. It's called the antiumbra here, and that's where we see an annular eclipse. And whereas the maximum duration we could ever get with a total eclipse of the sun is about 7.5 minutes, and offers a lot less, for an annular eclipse it can get up to about 12 minutes. And in this case, using the definitions that we had earlier, an annular eclipse could be considered to be a transit, a super transit. The third type of other eclipse, of course, is an eclipse of the moon. And this is a similar sort of geometry, but this time, whereas on an eclipse of the sun, the moon's shadow is cast onto the Earth, this time it's the Earth's shadow that's cast onto the moon. And typically, this shadow at the moon's distance is about 2.5 times the diameter of the moon. So these the eclipses of the moon last a lot longer than eclipses of the sun. When the moon is completely immersed in the umbra, it's called a total eclipse. When it's partially caught in the umbra, it's called a partial eclipse. And when it's in the penumbra, a lot of people forget about penumbral eclipses, but this, for reasons I'll explain later on. Now then, we would think that eclipses of the sun occur at new moon and eclipses of the moon occur at full moon. So why don't we get an eclipse of the moon every full moon, and why don't we get an eclipse of the sun every new moon? And to explain that, we have to have a little bit of terminology, a couple of diagrams, and then a couple of slides with some multiplication of numbers. Don't panic. I can see some people glazing over about this, but don't panic. It'll all come clear as we go along. First of all, a bit of terminology. The moon goes around the Earth, and we can define the orbital period of the moon against the background stars. And this is called the sidereal period of the moon. It's the sidereal month. However, the moon and the Earth move round the sun. So the next time the moon is lined up, say new moon, the Earth has moved round in its orbit, and it's in a slightly different direction. And this period to go from new moon to new moon is a little bit longer than the sidereal period. Sidereal period is about 27 days. We'll see the exact numbers in a minute. For new moon to new moon or full moon to moon, it's about 29 degrees. The other thing you'll notice from this diagram is that the direction of the sun from here is in this direction, and from here it's in this direction. So as we go round the sun seems to be projected against different stars on the sky. And it's almost as if the sun is moving around the Earth. I know that's not the case, but for the following discussion, it's a good idea to think of just the sun moving around the Earth. And its path it marks out on the sky is effectively a projection. I lost the microphone. Oh, okay. A projection of the Earth's orbit onto the sky. And this is called the ecliptic, where we get eclipses. Now, as I said, the sidereal period is that number 27.32 days, and the synodic period, new moon to new moon, is 29 days. Now, why don't we get an eclipse every full moon or new moon? It's purely and simply because the moon's orbit around the Earth is tilted relative to the Earth's orbit around the sun. And it's tilted by about 5.14 degrees. And this has all sorts of consequences of how we see eclipses. Most of the time, The moon will pass above, new moon will either pass above or below the sun from our perspective. And similarly for the moon will pass above or below the Earth's shadow from our perspective. To get them in line, we have to have them passing each other at a point where the two orbits intersect, and this is called a node. So if we have the Earth lined up with the moon and the sun also in line up, we'll get an eclipse of some shape or form. And these nodes are, there's two nodes, one where the moon moves from south to north, which is called the ascending node, and one where the moon moves from north to south is called the descending node. The other thing is that we'd think that to get an eclipse we'd have to be exactly lined up at the node, but this is not the case. Because the sun and the moon have both got finite angular diameters in the sky, there is actually a little window either side of which where eclipses are possible. And when we get in this window, these are called eclipse seasons. To complicate matters, astronomy is always complicated in some respects. These nodes are not fixed in space. They actually move, and they move in the opposite direction to the direction in which the moon and the sun are moving. Instead of going from west to east, these nodes are moving from east to west. And consequently, the lunar the time the moon goes from node to node takes a little bit shorter time. I'll just press the right button. And it's called a draconian month, and this is about 27 days. Also, because from our perspective, the sun is moving around the sky and takes a year, and the nodes are moving in the opposite direction. From one node back to the same node again takes the sun 342 days rather than 365. And this is called an eclipse year. So we've got these different periods running against each other. And now comes the fun part. We've seen that the period of the moon takes to go around relative to stars is 27 days or so. Full moon to full moon takes 29 days, and node to node for the moon takes 27 days. If we take 223 synodic periods, that's new moon to new moon, we get a big number. 6,585 days, which is roughly equivalent to 18 years, 10, 11 or 12 days, depending on when the leap years come in. However, if we take a multiple of the node-to-node months, the draconian months, it's almost the same number. Very little difference between them. Now, we've already established that to have an eclipse, we need to either be at new moon or full moon, and to be at a node. So if we have an eclipse which satisfies them conditions, we've got an eclipse, it's at the node or close to the node, 18 years, 11 days or so later, we're almost back to the same conditions. As you can see, the difference is very small. So we're likely to get another eclipse. This is very important. We get eclipses appearing every 18 years, 10, 11, 12 days after each other. And this period, this 11, 18 years, is called the Saros. It was certainly known to some ancient astronomers for predicting eclipse of the moon, but I think I'm correct in saying the actual term was coined by no less a person than Sir Edmund Halley of Halley's Comet fame. What's more, like I say, that's the synodic month. What's more, the month in terms of the moon going back from perigee to perigee, its closest, or apogee to apogee, is you take sort of 239 times that multiple, we get almost the same number again, the same Saros. Taking this all together, if we have an eclipse, 18 years later we get another eclipse, and it's almost in the same conditions. The conditions relative to the sun are shifted by 11 days, not very much, and it's almost the same type of condition where the moon is in its orbit. So if we get a really favourable total eclipse, we're likely 18 years later to get another favourable total eclipse. And similarly, if we get, say, an annular eclipse, we're likely to get an annual eclipse 18 years, so on. So there is 18-year repetitive cycle going on all the time. So far, so good. And we'll find that over a period of time, these cycles appear and disappear over a period of about 1200 to 1600 years. This means that, like I say, we can illustrate this by looking these are tracks of one Saros cycle, which is repeating every 18 years or so. And certainly I think the most famous one for everybody in here was the one in 1999 that crossed the UK in Cornwall. And that's the track, you can see it goes along there. 18 years later, we get another eclipse, which is in 2017, and this is across the States. And if I may just go back to the previous slide, you notice this 18-year cycle and 11-day cycle is not whole number, it's about 1/3 of a degree. So when we get to the next eclipse, the Earth has rotated almost through 120 degrees. So the track moves westwards through 120 degrees. And we can see this here. This is the same track that crossed the States, moved from the one with the UK. You'll notice also that it's further south, and I'll explain why in a minute.
Could we try a re-mic? We are actually losing.
Oh, okay. Do you want to time out, take a breath, cup of coffee?
Temporary.
I thought it had gone quiet.
I'm not sure whether the button's
Okay. Is that any better? Give it a go. Can you hear me? Right, that ends the commercial break. So we were saying that these tracks move, in this case, has moved south, and this is when, and the next one is even further south and moved 120 degrees west towards China. The 2017 eclipse is interesting because there's one or two that have occurred in the States over the last few years. There's one in last year in the States. And for the 2017 one, a certain leader who will be nameless, his surname ends in UMP, was thanking NASA for providing the eclipse over the States. As wonderful as NASA is, it's an exemplary organisation. Even they haven't got the power to change the moon and its orbit. It's all down to celestial mechanics. Now, this will be the last complicated diagram, and I assure you. What I mentioned that eclipses appear in this window. And we can sort of envisage that this shows the track of the moon, the path of the sun, the ecliptic, the track of the moon for an ascending node. And we can almost imagine a condition where the two disks, from our perspective, are just touching either side of the white circle represents the node, and just touching here. So we can imagine that any eclipse within this region, more and more of the sun will be covered up. So these mark a boundary. Outside the boundary, there's no eclipse. Inside the boundary, there will be eclipse. And we can define what these boundaries are. We have to use spherical geometry to define these, but if you work through the sums, we find that there's two sets of limits. One is when the sun and the moon are at their smallest, because distance from the sun and moon Earth changes, and one at the largest. And these distances are actually quite big. For a minor, what's called a minor limit, for a total eclipse, an eclipse of the sun, it's plus or minus 15 degrees or so. So there's actually a window stretching 30 degrees along the ecliptic where eclipses are possible. And in fact, there's an outer limit, the major one, is where the sun and the moon are at their largest. So we have to define two. Now, here's another fun thing. If we put the sun and the moon, say, at this point here, where there's no eclipse, they're just touching, the moon takes 29 days to go from new moon to new moon. But the sun, relative to the node, going across this boundary, will cross it in about something like 0.1 or 0.2 a day, I can't remember the exact number, a bit longer. And the implication of that is, no matter where the moon is in the sky, as soon as the sun enters this region, the moon will catch it up and produce some form of eclipse. And certainly with the wider limits, it's even more possible. And sometimes we can actually get, say, an eclipse that appears at this end side of the node, and there's sufficient time for the moon to go round in its orbit and catch the sun up before it exits that, and we sometimes get two eclipses in one node. The bottom line is that we're always guaranteed two solar eclipses every year, one at each node. That is how it always works. And sometimes, we're talking predominantly about the sun, but if you can imagine the moon goes into eclipse on the opposite node, there is sufficient time sometimes that we might get a pair of eclipses, one of the sun and one of the moon, perhaps one out before or one after, because the sun and the moon have got time to go round, and the moon's got time to go round and catch the sun up again inside these windows. That's a difficult concept to grasp over, but this is how it works. We've got these windows either side of the node, and we can get things. In fact, we've got a good example that was illustrated earlier. We've got an eclipse of the moon coming up in a day or two's time, and an eclipse of the sun in 2 weeks' time because of these windows around the thing. The final thing, and this will be almost the last of the mathematics stuff, is that on an ascending node, the eclipses start here and they run through, separated by about half a degree, and then the next eclipse will get total, and then we get to near the node, and then we get a series of eclipses that go like that. So there's a family of eclipses that will go as they move across from east to west across this eclipse window. And so if you do the sums, it works out that we can get a family of eclipses lasting over 1,000 years, 1,400 years, something like that. And they start off at this end, start off as partials, we eventually get into totals around here, and finish at partials again. The other thing you'll notice, with the moon being up here, the shadow will be projected towards the north. And down here, the shadow will be projected towards the south on the Earth. So as the cycle evolves, for the ascending node, it moves from north down to southwards. And for the descending nodes, it goes in the opposite direction. And here's this diagram again we showed as Mr. Trump's eclipse, and you can see why these are moving southwards, because these are of one of these, the ascending nodes. And the opposite goes for the other thing. So we get all these families of eclipses running on for 18 years and years. And there's also about 20 or 30 of these Saros cycles running at the same time. So this is why we get this complicated pattern of eclipse tracks. But why? That's the maths over with. I can see the sigh of relief from everybody. So if we're seeing a total eclipse, what are they like? What have we got to do? Well, as we've seen, that certainly for total eclipses of the sun, they're visible from narrow tracks. So it usually means that for the majority of people, they have to travel. And as much of the surface of the Earth is water, 70% or so, a lot of the tracks will go over water, which was very difficult years ago. But nowadays, holiday companies have latched in onto this, and you can get cruise ships. But deciding where to go, there's a lot of things that are things. There's obviously the political situation. You don't want to go to a country that's hostile and natives are restless, so to speak. The climate is very important for everything. Disease, inoculations. Another important thing is where you decide to go is the totality duration going to be a good one on that particular eclipse? You know, it can vary quite considerably. And then, of course, there's the cost of getting there by modern day travel and local terrain. But as you might have gathered, the most important criteria is the weather. And this is a cartoon for the 1999 eclipse, one of the papers, and you can see it was not very favourable. But climate is very important. And we all know about weather in this country, and there are websites that produce cloud statistics for any location. And there was an eclipse in the States last year, in 24, and the best place to see it was from the west coast of Mexico from a weather point of view. So a lot of people went there, and it wasn't cloudy, but it got a little bit hazy, which stopped seeing the outer corona. Other people went to Texas. They had more things where it was a little bit more stressful. Many people had cloud until about a minute before the onset of totality. It cleared briefly. And other times you can go to places, and even if the weather prospects are good, you end up with it's raining. So it is a bit of a lottery to where you go. So, equipment. Well, we'll talk about equipment for saving your eyes later on, but during totality, there's so many things going on. And I always think sometimes that it's nice not to just observe it. And some people go to take photographs, and I've seen people turn up with so many cameras and telescopes to operate them. And I've seen people say, what a great eclipse it was. Didn't see it because I was operating all the gear. So, you know, it swings and roundabouts again. Nowadays, with modern digital cameras, you can probably program them. But certainly for an eclipse, a pair of binoculars is great. You obviously can't look without protection during the partial phases because of damage to the eyesight, which might turn up, so I'll talk about that a bit later on. So, we managed to get to totality, a total eclipse of the sun. We go through all the partial phases, sometimes there's sunspots, sometimes they're not. But then we get to where it's almost totality. And at this point, the crescent is very narrow, and lots of things are going on at the same time. It gets dark, but not pitch black. It's nothing like that sci-fi film Pitch Black with Vin Diesel where it went completely dark. It's like very heavy twilight. Imagine if you can see the brighter planets in twilight. It gets that dark. Another thing that happens is that the sky may darken from the west, which is the onrushing umbral shadow, which is moving at a hell of a rate, about Mach 2. Something like that. I mean, some of you may remember when they sent a Concorde up to chase an eclipse. That was the only aircraft in the world that could keep up with the speed of the shadow. Looking on the ground, you're obviously looking up there, but occasionally glance to the ground, you might see sort of ripples going along the ground. These are called shadow bands, and they're not completely fully understood, but because the crescent is very narrow, it's been disturbed by atmosphere, similar to stars twinkling, and you get all these ripples along the floor. But the main thing it's observing is when the last vestiges of the crescent start to disappear, and we end up with something like this. To get this sort of picture, the sky looks black because you're shooting something that's relatively bright, so it's misleading. And what we see on here are what are called Bailey's beads. The last vestiges of the crescent of the sun start to bake up. And this is purely because of the profile of the moon. We've got craters and mountains seen in profile, and they break up the light. And over time, this gradually begins to disappear and break up, so eventually the photosphere, the bright area of the sun, is almost disappeared. And we sometimes start to see now prominences, these things that can be seen with, sorry, I'll just go back one again. It's remote, it's a bit opposite to what I'm used to. See prominences around the disk, these are gases of hydrogen that stick out, and the red chromosphere. And if I just run this back again, you can see how quickly this changes. In a sort of matter of seconds, where the Bailey's beads break up the last vestiges of the photosphere. The beads, incidentally, are named after a guy called Francis Bailey, who first observed them. And then we're left with the prominences. We saw earlier in a couple of photographs that nowadays you can buy telescopes that have frequencies in hydrogen and alpha wave band, and you can see the prominences anytime. But prior to these were the only times we could really see prominences was during a total eclipse of the sun. And depending upon activity, might depend on what prominences you can see. And certainly in the long eclipse in 1991, there was a huge prominence came off the sun, looked like a sort of seahorse thing. And that's certainly one of the bigger ones that's happened over the last few years. The outer atmosphere of the sun is the corona, and this is really the thing that many people see. It's quite big, it's very bright, and as you can see on this, it's got all these sort of tendrils in it because of the magnetic field of the sun. It would seem that when it gets solar maximum, this corona tends to be fairly symmetrical, but at solar minimum, for whatever reason, it gets more asymmetric. And photographing this, you need longer exposures, and if you take a lot of exposure, if you're taking pictures, you'll overexpose the inner corona to get the outer corona, and so on. But sometimes people make up fancy composites. Down here you can see a star. It's the bright star Regulus, the brightest star in Leo. And as I said, you can sometimes make up composites to show the tendrils inside coming off in the corona. And this is certainly until relatively recently, perhaps 50 years or so, total eclipse of the sun were the only time that we could really study the corona like this. Sometimes you get lucky and you might get bright stars or planets near to the sun. And this particular one shows Venus and Jupiter nearby. We always think photographs don't really show what you actually can see. The naked eye is a wonderful wide-angle optical instrument, and this could be seen up in the sky with the surrounding terrain, and no photograph really can capture that. But sadly, things come to an end, and the eclipse is starting to come to an end. And I have a friend, a guy called Sheridan Williams, who has written a few books on eclipses. And he says, well, I've said that, you know, eclipses can be a few seconds long, be up to 7.5 minutes long. He maintains that all total eclipses are of the same duration, because they all seem to go by so quickly, it's gone in a blink of an eye. But there we sort of see where the sun is starting to reappear again. The moon has moved this way, so exposed this prominence, and very quickly we get the Bailey's beads again at third contact, and that is rather nice. So total eclipse of the sun, I think, are really spectacular. But we also can get annular eclipses. You don't see the prominences of the corona because we can still see the bright photosphere of the sun. And you get something like this. The width may vary a little bit depending on the size of the moon relative to the sun. And they're really basically souped up partial eclipses. Eclipses of the moon are also interesting. They're not as dynamic as eclipses of the sun, perhaps not as bad, but I still think they're rather beautiful things to see. And I mentioned earlier we get penumbral eclipses, and these are not that easy to spot. And I don't know if you can see, oh, sorry, I jumped again, wrong way round. You can see that there's that sort of shadow, that's the penumbral shadow on the moon. And I always find it a bit easier to see with binoculars or taking a picture. And you can see that it's slowly moved that way off the moon. And they're a little bit difficult to spot, but a proper umbral or partial umbral eclipse is certainly the sort of thing that's well worth seeing. And here we can see the umbra coming onto the moon. It darkens the moon. That's the shape of the shadow cast by the Earth. And if you take pictures, you can either expose it correctly for the full moon and underexpose that, or get a little bit longer exposure and overexpose that. And gradually the shadow then comes to the moon, so we get a total eclipse of the moon, something like this. And we've already seen pictures of these as well. And these can sometimes vary in brightness. You would think that when the moon goes into the shadow, that's it, you won't be able to see it. But the Earth's got an atmosphere, and this atmosphere scatters blue light radiation. That's why we get blue skies. But longer radiation, such as red light, is less scattered and is refracted onto the moon. So we get this sort of red coloration. And depending on how much crud, volcanic dust, other things are in the atmosphere of the Earth, it can either be quite a bright eclipse or it can darken it quite noticeably. And I've seen one lunar eclipse where it just looks like a ghostly ring in the sky because there's been stuff in the atmosphere that's darkened the moon. But we can see eclipses from other worlds or on other worlds. And this is a picture taken by one of the Mars rovers, Curiosity, and there's several pictures of this, both the larger satellite, Phobos, and the small satellite, Deimos, going across the eclipse in the sun as seen from Mars. And these are like souped up annular eclipses, really. But probably one good place to see eclipses from is the planet Jupiter. And it has the four largest satellites, Io, Europa, Ganymede, and Callisto. And they go around Jupiter and can go into occultations, which we can see where Io is going behind the planet, or they can go into transit, where you can see the satellite and its shadow, and here we can see the largest shadow, Ganymede. And if we could stand on the surface of Jupiter, we'd see quite good eclipses, because I think I'm correct in saying that from Jupiter's surface, all these four satellites look a lot bigger than the sun, because Jupiter's much further away from the sun, so the sun is smaller. The only problem with that from Jupiter is its intense radiation environment around the planet. You certainly need your lead underpants on, so to speak, for something like that. And similar things can sometimes be seen on the other giant planets as well. But we do get eclipses. And this animation is Jupiter. If you wait a minute, if you look here, you eventually see something appear. It takes a little while to do. And this was taken on a dodgy night through cloud. Everything had to be turned up. And eventually, and I can't remember how long this will take now, you might see something start to appear. I hope it doesn't run too long. Something in this area. And what you're going to see is one of its satellites, Europa, reappearing from eclipse. Come on. It seemed so quicker when I ran this morning. Yeah, there you go, you can see it now. You can just start to see it brightening up. And this is coming out of the shadow of Jupiter from the umbra and penumbra, and it gets up to full brightness. But an eclipse like this had an important thing in the history of physics. And the geometry, let me explain this, is obviously not to scale. We've got the Earth going around the Sun at various points, and we've got Jupiter over there with one of its satellites. If we're in a line where the Earth is at its closest to Jupiter in its orbit called opposition, then we'll probably see the shadows cast by the satellite onto the disk, but we can't see the things going into eclipse because the planet's in the way. But from this side or this side, we get a view of the shadow, even if we can't see it, and we can see eclipses taking place. And sometimes we can see the satellite disappear or reappear from eclipse, and sometimes for Ganymede and Callisto, we can actually see them go into an eclipse and then go behind the planet. But it was in the 1640s, 50s, can't remember the exact date, probably a bit later, at the Paris Observatory, which was under the directorship of what was an Italian astronomer who went to work in France, called Gian-Domenico Cassini, and he changed his four names into the French version, so we better know him as Jean-Dominique Cassini. Cassini, I'm sure all of you have heard of his name for the famous Cassini division in Saturn's rings. Working with him was a Danish astronomer called Ole Rømer, and they had been studying the times of the eclipses of Jupiter's satellite Io, like Europa we saw there, a similar sort of thing. And they were finding that around opposition it meet predictions, but when it was further away, the Earth was around this point and observing, they found that the times of the eclipses were out of sync, they were later. And Rømer suggested that perhaps this is because light wasn't instantaneous, it had a finite velocity, and the difference was because it had a longer track to go across the orbit of the Earth when the Earth was at this point rather than here. And he made an estimate of the speed of light. I think it's about 2/3 of the modern day values. But this was an interesting observation which an eclipse contributed to. Eclipses occur even further away with stars. Some stars orbit each other, and from our perspective we sometimes see the orbit in the plane of which the two stars are going around each other. And we get what were called eclipsing binary stars. And perhaps the most famous one is a star called Algol or Beta Persei. It's in the constellation of Perseus. It's quite bright, easy to see with the naked eye, and every so often it drops in brightness from about magnitude 2 down to about magnitude 3.4. And the total cycle takes 10 hours. And again, this is a sort of eclipse. We've got two stars going around each other. One is smaller and brighter, one is larger and a bit fainter. And when the small one is in front, we get a small dip in brightness. But when the dark one goes in front, we get a deep drop in brightness. And study of these periods of eclipses gives astronomers ideas about the size of the orbits and other things as well. Eclipses have been observed for a long time, for lunar and solar eclipses. And often as not, they were viewed with suspicion, fear and dread, which is not surprising really. Eclipses of the moon can be seen from quite a large hemisphere, and even though they're less frequent than total eclipses of the sun, to see the moon suddenly drop in brightness and turn blood red must have scared the living daylights out of people who perhaps didn't understand what was going on. And certainly if you were in the path of a total eclipse, that would be even worse, where the sun disappeared. So a lot of older cultures didn't fully understand what was going on, thought it might be gods, demons, dragons, anything else, and they'd come out and bang gongs, etc. to do this. So it's often treated with something of fear and dread. In fact, even Shakespeare noted something about eclipses in King Lear. These late eclipses in the sun and moon portend no good to us. Again, it's sort of portending some sort of evil and anything. But eventually people understand what things. But the first recordings of eclipses, although probably people had seen eclipses years before that, were by the Babylonians, and in their clay tablets recorded various eclipses. And it certainly seems likely several hundred years BC they actually started to be aware of the Saros period for eclipses as well. But other things, sort of mystical things, have also cropped up. And I don't know this is true. This is a story that's often said about eclipses involving two Chinese astronomers, a Mr. C and a Mr. Ho. And it could be a fairy tale, it may not be. But apparently these were astronomers at the time, and their job was to try and predict and everything, they didn't predict an eclipse that occurred. The emperor was very upset, and you can imagine what happened to these two guys. It wasn't very pleasant. This might be a fairy tale, I don't know. But certainly one thing of use of eclipses where one group of people of influence is another occurred with Christopher Columbus, no less, in Jamaica. I think his boats were stranded. They were getting help from the locals with wood, but he realised an eclipse of the moon was going to take place, and he tried to convince them, he had words with his gods, that the moon would turn red if they didn't help him. And the moon did turn red in an eclipse of the sun, and they finally decided to give him some food and so on. But perhaps of all the eclipses that have taken place throughout recorded history, there's one that is probably the most famous and most important. And it involves this guy. And I haven't put a caption on it because this must be one of the most famous people in history, Albert Einstein. And with his theory of general relativity, which in the end was published in 1916 during the Great War, the First World War, I make no pretense whatsoever. Relativity, boom, over my head. But one of the things about relativity, it came up with this concept of space-time. And this is a thing that's often said in the books, and this is as far as I know, that matter distorts space-time. But the distortions in matter tell matter how to move. So this is Einstein's view of what gravity is, this distortion in space-time. And when he first proposed this theory, it worked for the planet Mercury. Mercury's orbit, its perihelion, aphelion, were turning slowly in space. And the great French celestial mathematician Urbain J. Le Verrier had worked out all the influences that were on Mercury, and he'd come to account for some of the small precession that was going on. And he actually proposed another planet, the so-called Vulcan planet, not Mr. Spock's Vulcan planet, that was causing this effect. That planet didn't exist, but Einstein's theory of gravity explained the precession of Mercury's orbit very well indeed. But another idea was that this distortion in space-time would distort the positions of stars if they passed near a massive body. And the nearest massive body to us is the sun. So Einstein had proposed that maybe we could observe the bending of starlight during a total solar eclipse. There was one that a few years earlier when this was done didn't work. And this is the idea that a star light passes near the sun, but actually appears here. The angles are very small. So, enter one of the great British scientists, Sir Arthur Eddington. He was a brilliant scientist, but he was also a Quaker and a pacifist. And of course, at that time, just 1918, 1919, was the Great War, the First World War. And conscription was looming. And the astronomer royal, Sir Frank Dyson, was hoping to keep Eddington away from conflict. He was a brilliant man. Eddington sort of blotted his copybook a little bit, where he got a bit annoyed with some of the papers. He had to sign something and refused to do, say he was a pacifist. That was his reason not going to be conscripted. And Frank Dyson had to make some influence to keep Eddington on not go to war, so to speak. But they decided that we're going to try and prove Einstein's theory by going to observe an eclipse, which took place in 1919. And this is the path of the eclipse. It started over South America and ended over Africa. Two teams were sent. One, Mr. Cromlin, was sent to Brazil, and Eddington went to an island, I think it's called Principe, just off the coast of Nigeria, to observe this eclipse. And the idea was they would photograph the eclipse to try and detect some stars, and then photograph the same area of the sky a few months later, and then see any changes in position. Fortunately for them, the eclipse took place against the background of the stellar cluster, the Hyades, which is in Taurus. It makes that V shape of the head of Taurus, so plenty of bright stars. And the team in Sobral in Brazil, I think, had a few mechanical problems with the telescope. But for Eddington, he had the same thing that happens for a lot of eclipses. It was cloudy and raining before the onset of totality. he managed to get a few plates, and it was plate film, not any other, it was plates into the camera to take some exposures between the gaps in the cloud. And here was another person who never actually saw the eclipse. He was so busy changing his plates. And a lot of the plates weren't good, but a few of them worked, showed some stars. And this is one of the plates that he got. He got the corona. I don't know if you can see there's a couple of marks where he marked the positions of the stars. A few months later, they rephotographed the sky and measured the positions of the stars during the eclipse and after the eclipse as accurate as they could. And he found that the positions of the stars during the eclipse had moved slightly. Newton's theory of gravity implies that this can happen as well. But Einstein's theory said it would be twice as much, and they found it was nearly twice as much. And so, at a meeting in 1919 at the Royal Astronomical Society, Royal Society joint meeting, they announced the results, which caused a lot of celebration for Einstein's theory. Subsequent revisionist history say these results weren't as good as perhaps Eddington claimed, but subsequent measurements say they weren't perfect, but were good enough to give an indication that Einstein was right. And subsequent eclipse measurements have shown that Einstein was right. But there's an oft-told story, I don't know if it's apocryphal or not, about Eddington. Obviously, the reporters were all over Einstein and Eddington after these results were announced. And this reporter apparently said to Eddington, Mr. Eddington, you're one of 3 people who understands general theory of relativity. And Eddington sort of paused for a bit and the reporter said, what's the problem? He said, well, I'm trying to think who the 3rd person is. So that may be true, I don't know. But eclipses, as you can see, have had a big effect on science. Nowadays, of course, we don't necessarily have to go to eclipses to study the corona and the prominences. So earlier you can buy prominence telescopes in hydrogen alpha to see the prominences. And in 1931, the great French astronomer Bernard Liot developed what he called a coronagraph. It was a device to obscure the central disk of the sun, the photosphere, and reduce scattered light so we can get pictures of the chromosphere. And these have been used subsequently in all sorts of applications, looking at features, stars to see if we get planets close by, and they've also been carried by spacecraft. And perhaps the most big workhorse of solar studies, I know we've got the Parker Solar Probe, Solar Orbit, is the Solar and Heliospheric Observatory, better known as SOHO. And that's got a coronagraph inside of it, and you can see on these pictures, you can see quite the background stars, sorry I keep doing that, the stars showing the corona and background stars as well. So nowadays, perhaps the need to go to total eclipses for studying the sun is not as great because we've got all these fantastic instruments, but it's still a good thing to see. We've already aired earlier that we've got 2 eclipses coming up. We've got a total eclipse of the moon coming up in just under 2 days' time, which is good news, but as we've already heard earlier, it's not quite favourable. The times here show when the greatest eclipse is going on. As we've always seen earlier, the greatest eclipse will be after the moon has set. And this shows the night sky in the early hours of the morning, just about the onset of the umbra coming across the moon, just before the moon sets. The moon is sort of south of Arcturus, and you will need a good horizon, or preferably an elevated horizon, unless you've got a very tall house with a window on top that looks sort of southwest to see this, but it's still worth having a go. Prior to that, it was predominantly penumbral in eclipse, and it was seen earlier, the penumbral phase is quite faint. We've also, and this shows a simulation of what we'd see in the morning before the moon sets. That's where the umbra will be, coming from this side towards the Mare Humorum, and so on. We've also got a partial total eclipse, which we've alluded to earlier. The timings are approximate. This is from my place, a simulation from my place, but give or take a minute or two. This is where it'll start. We'll sort of start about 10:09 and finish just about midday, and that's the simulated track of the moon. And hopefully there'll be some sunspots there, and people with H-alpha telescopes will maybe be able to see some prominences as well. Eye safety for total eclipses is very, very important. And if I may, I just spotted these here, if I can just grab one. The sun is incredibly bright if you look at the sun for any length of time, you're going to damage your eyesight. It's not worth it. And so certainly during the totality for eclipses of the moon is safe. During totality it's safe, but it's during the partial phases that you risk damaging your eyesight. So there are various ways of getting around this. There are, you don't have filters at the eyepiece end. They will shatter because of the heat from the sun through the telescope. So you can get metal on glass filters, which are quite expensive, or you can get mylar filters that can fit on the front of the telescope. These are very similar to what you get in these eclipse glasses, but you have to make sure there's no tears or pinholes in them. And these are probably the safe things to look for observing the partial phases. I mentioned the hydrogen alpha telescopes, but they're rocking expensive. And then we can have projection. This is the simplest way of observing the partial phase. And this is my partner Valerie. She has absolutely no interest whatsoever in astronomy. Absolutely, she puts up with me very patiently. Well, there was an eclipse of the sun a couple of years ago, was it 2016? I can't remember now. It was cloudy down here. We took the day off work and we decided to go up the A1 where it's a bit clearer, and we ended up in a car park off the A14, unloaded all our gear, much to the consternation of East European lorry drivers. But this is Val with a tiny telescope, the car to shield that, and you can see you can project an image of the partial phase onto a piece of card. That's by far the safest and easiest way of observing a partial eclipse. And if you haven't got a telescope, you can go one step further and replace the telescope by a pinhole and project that on to the eclipse, see the eclipse as well. So that is a simple and easy way of observing the partial phase. You don't need expensive things, and these things are good as well. Time's almost up. Yeah. There are other eclipses this year. Again, we've got two, an eclipse of the moon and a partial phase within a sort of 2-week window. The partial solar eclipse is not visible from here. It's in South America, Antarctica. But we've got another total eclipse of the sun on September the 7th, and in many ways it's a complement to the one that happened in a day or two's time. And I put the times of where things happen. In this case, we've got the moon is rising just after the greatest eclipse. So in this case, we'll be able to see a good portion of the eclipse after. So if I just go back one slide, the moon will be rising, and then we'll have the moon leaving the umbra, and then the. So we'll see quite a bit of the eclipse on this date. And again, it'll be rising about sort of 7 o'clock in the evening. That is Greenwich Mean Time. The clocks will probably still be on British Summer Time, so it'll be 1953 if you're using British Summer Time. And you'll be able to see the moon rising and just come out of an eclipse. So that'll be one that we're looking forward to. And next year there's a total eclipse of the sun that crosses Spain at the end, so that's one worth looking out for as well. Eclipses. These are they produce anything that passes in front, whether it's a transit, occultation or eclipse, can produce immense scientific information by just one body passing in front of another. A good example of this was in the 1960s, I think it was, when quasi-stellar objects, these radio sources known as quasars, were discovered, and radio telescopes at the time couldn't pin down the exact position. And the moon was passing near this area several times, producing occultations. And by measuring these positions, they've got an accurate position where this quasar was, so they could see in optical wavelengths. Eclipses of the sun have produced exciting scientific results as well. And nowadays, if you think of one object going in front of another, we think of exoplanets and the transits of the main system that are used by many spacecraft to discover exoplanets. But also, I think any object movement produces a really beautiful event that we can all enjoy. Sometimes, in case of a total eclipse of the sun, something very, very spectacular. And certainly, I hope that it's going to be clear on Friday morning and a couple of weeks' time on Saturday, so we can enjoy 2 eclipses. And with that, ladies and gentlemen, thank you very much for listening.
Does anybody have any questions that they'd like to put to Mike?
I'm very interested in going to view eclipses.
Yeah.
And when you do that, do you just make your own trip, or do you usually go in a group?
Bit of both. Bit of both. Sometimes it's easy to go in an organised tour, and there's plenty of companies that will take your money and take you to any location in the year. Sometimes I've done it myself, certainly with the States. I've done Eclipse of the States ourselves, and that sort of works out reasonably well. It's you have to do a lot more effort to get there, but it might work out a bit cheaper. But certainly a lot of the companies that do these eclipse trips are usually very good and very reliable and get you on site, which is the main thing.
You talked a lot about the kind of scientific part of eclipses, but what does it feel like to be part of one and viewing it from a kind of a human in the universe?
I think everybody is different. Everybody reacts differently, so I think it'd be difficult to generalise. I think it's just to see the sun disappear is pretty good. Like I say, it's so easy to get caught up cameras, and I think certainly over a number of years, take a few pictures, but the key thing is to enjoy it. If I may give a slightly sort of personal observation, my partner Valerie, like I say, she's not interested in astronomy, but came out for one eclipse. She's never seen one before, and she said it was great, and then a day later she said she burst into tears when the last bit where you see the moon moving off the sun, you get the Bailey's beads making what is called a diamond ring. So everybody reacts differently. I've also known the converse argument, one in India where you go and see the Taj Mahal, and someone who said to me that he preferred the Taj Mahal to the eclipse. So horses for courses, really.
Well, I was personally really amazed by this for two reasons. One, by physically what we had seen, but the other thing was that we knew in advance that it was going to happen and at what time. Future plans? Well, there's one in the northern coast of Spain next year, except that totality is almost at local sunset, and it's 2 minutes 40 seconds, which isn't, well, it's good. But no, I'm going to wait for the next year, and I plan to go to Luxor, because you can fly direct from Heathrow to Luxor. The town is 15 minutes drive from the airport, and the central line of the eclipse track goes over northern Luxor.
Yeah, so Jeff Bryant says, really interesting presentation, which I learnt a great deal. Do you have any recommendations? Who are the best people to contact to arrange a trip to Spain in 2026? Alternatively, is there a chance that Hearts Astro Group could organise it? I can answer a little bit of that. My question to you is, did you take those pictures yourself? Yeah, in your presentation. They're fantastic. Yeah, they're really good.
I think we've had a great experience this evening, and for some of us we have some great opportunities to look forward to in the future. So can we please show our appreciation for Mike? Thank you.
One's a bit better. Okay, as I say, thank you very much, Mike, for a super talk there. Just a few announcements. And on the 29th of March, we've heard there's an eclipse. We are hoping to set up in Hertford Castle grounds. The eclipse is from 10 till 12. We've been given permission to go there, so from 9 o'clock onwards, come down there. Even if you're not going to be able to show the eclipse, and there's no reason why you shouldn't, we've seen some interesting ways you can project it, but you can also promote the club. Free parking in the castle grounds, that must be worth something. Again, we need the volunteers to show the eclipse and to promote the club, so we'd be delighted to hear from you if you can come along to that. Our next meeting is April the 9th, when we got David Southwood talking about a decade as an ESA director. Other than that, can I say thank you very much indeed to the technical team. Thank you to all the other committee members who have made this evening possible. And of course, thank you again to Mike. All that needs to be said to all of you is have a safe journey home, and we look forward to seeing you again soon. Thank you and good night.